All right, here's the answer key to the assessment readiness test for target 46, which is factoring quadratic expressions. When you're looking to factor quadratic expressions, the first thing you want to do is look and see if any greatest common factors can come out. So I'm just going to kind of pull through these questions first. That one, there are no common factors. There are no common factors of all three of those. 9 is a factor of the first two, but not the third one. No common factors. Here there might be. I'm going to show you a way around that one because there's a shortcut to it. And then this one, none. This one, again, there might be, but there's a shortcut that makes that a little easier. So the other thing you're going to want to do is if there are some shortcuts, that will be evident by one of two things. If you look at the terms, and particularly the first and the last, they are perfect squares. Square root of 36 is 6, square root of 64 is 8. There's a shortcut to that one. This one has a shortcut for a couple of reasons. First of all, this is a perfect square and 1 is a perfect square. But also, anytime that leading coefficient is 1, there is a shortcut way to do that. This one has a shortcut because those are both perfect squares, and there's another criteria that has to be true, but usually when that happens, there will be a shortcut. These are perfect squares, so there's a shortcut there. 7 and 2 are not perfect squares, and the leading coefficient isn't 1, so there is no shortcut to 7. Likewise, there's no shortcut to, 13. And there's no shortcut to 12. And there is a shortcut to number 11 because the leading coefficient is 1. So I'm going to start with 12 because all of them can really be done in this method, but it takes longer. And to finish the test, you're going to want to get proficient at some of these shortcuts. But again, this method always works if you get stuck on a problem. So we're going to start by making the box. And the first and last terms are going to go in the corners of the box. And then you ask yourself the magic question. I need two things to fill the rest of the box that add to 18x and multiply to the product of 9x squared and 5, which is 45x squared. So I multiply the 9 and the 5. So I start using my head a little bit and start thinking of factors of 45, like 1 and 45, 2 is not, 3 and 15. And I could keep going with this list, 5 and 9. And I'm looking for the factors that add to 18. And I can see that these two add to 18. So I need to put those, actually be a 3x and a 15x to add the 18x. So I put those in my box, and it doesn't matter which place they go. You could have switched those around. After you do that, then it's just factoring out the greatest common factor from each row or column. So going up here, this row, I can factor out a 3x per column. This column, I can factor out a 5. Going this way, I can factor out an x, actually a 3x. And going this way, I can factor out nothing other than a 1. And then if there's any plus or minus signs, deal with those at the end. So this is going to factor to 3x plus 5 times 3x plus 1. And you can double check with multiplication. It multiplies to 9x squared, 15x, 3x, and 5, which combine to 9x squared plus 18x plus 5. All right? So we do that same thing for number 13. Because again, there is no shortcut for this one. 7x squared, 2. So the magic question is what adds to 15 and multiplies to 14. So I start thinking of my factors of 14, 1 and 14, 2 and 7. Oh, I found it right away, 1 and 14. So I'm going to put 1x and 14x here, factor out my GCFs. X, oops, excuse me, 2, 7x, and a 1. Double check that everything multiplies out. There's no negative signs to worry about. So my answer is going to be x plus 2 times 7x plus 1. You could flip the order of that and have 7x plus 1 in parentheses times x plus 2 in parentheses. All right? Now, if I go back to number 1, I could do the same thing. But the shortcut here is, since the leading coefficient is 1, to get my x squared, I'm just going to start out with an x and an x. And the magic question, you'll have to add to that and multiply to that. Those two, the answer to the magic question just go here and here. So I need two things that add to negative 12 and multiply to 27. So I'll think of my factors of 27. Well, 3 and 9 add to positive 12, so if I want them to add to negative 12, I'll make them both negative. Negative 3 plus negative 9 is negative 12, and they add or multiply to positive 27. And that's the factorization. Done. If you had done the box, it would work. Okay, you'd end up with x squared, 27. Your magic question would be negative 3x and negative 9x. So you'd factor out the x's and the 9 and the 3, and then to get the negative here in these two spots, put positive in the bottom right, you'd have to put negatives in both. Okay? Now the other ones with the perfect squares have different shortcuts. And again, you could do these with the box method, but you're going to get really big numbers, and I think it's going to take you a while. If you see perfect squares, I want you to start by square rooting those. So if I square root 81, I get 9. Square root of n squared is n. If I square root this, I get 6. Now, in order for the pattern to work, the product of those two, which is 54n, doubled should equal the middle term, which it does. So the rule then is it's just going to be 9x plus 6 used as a factor twice. And you could check your multiplying with the box method. So this is the answer, which could also be written as 9x plus 6, the quantity squared. There's a direct connection to some of the problems on this target that were on the previous target, 45. This is basically just the reverse process from target 45. Likewise, this one. Square root of 49 is 7. Square root of x squared is x. Square root of this is going to be 5y. If I multiply those together, I get 35xy. And if I double that, I get 70xy. So I almost get the middle term, except it should be negative. So to make it negative, my two factors are just going to be 7x minus 5y times 7x minus 5y. Or, more simply, 7x minus 5y, the quantity squared. So same thing as the previous one, just with a minus. Now this one is called the difference of two perfect squares. If you square root the 1t squared, you get 1t. If you square root the 49, you get 7. But you notice there's no middle term. So in order for there to be no middle term, you can think of this, if you were doing it with the box method, what adds to negative 49 and multiplies to 0. Excuse me, what multiplies to negative 49 t squared and adds to 0t. So the two numbers that multiply to negative 49 and add to 0 are going to be 7 and negative 7. If they add to 0, they have to be opposites. So the factors, you just take your t and your 7, you do one factor with a plus and the other factor with a minus. And that will make it so the middle term cancels. By middle term, I mean if you had written this one out like this. That middle term is 0. Okay? So this is your answer here. All right. And then number 17 is real similar to that. These are perfect squares, so if I square root this, I'm going to get 6t. If I square root this, I'm going to get 8. There's a 0 in the middle or nothing in the middle, so it's going to factor to 6t plus 8 times 6t minus 8. However, I did say, because this isn't technically the correct answer, because it can be factored further. So to factor it completely, I can either factor out from here, I can factor out a 2 from each of these. So I get 2 times 2 is 4. Or if I would have factored out a 4 first, so it would have been 9t squared minus 16 from the original problem. And then if I would have square rooted these, I get 3t, square root of this is 4. And I was looking back, I see I did have one other one that I didn't completely factor because I forgot to factor out a GCF first, and that's number 14. So number 14, I could have factored out a 9 from everything here first, but I'm left with 9n squared plus 12n plus 4. And I still have perfect squares, so the pattern is still going to work out. It would be 3n plus 2, 3n plus 2. So this is technically the correct fully factored answer. I could have factored out a 3 from my final answer here as well. Factored it out from each of the two. And 3 times 3 gives you 9.